Imagine trying to catch a 14-story skyscraper as it falls from space. To a handful of recovery teams around the world, that is just another workday. Far from the launch pad, the real magic of modern rocketry happens over open ocean. Welcome to Beyond Delta 5, where we dive into the secret world of rocket recovery. Today we will follow boosters from the edge of space back to hidden refurbishment hangars. We will see how catching and reusing rockets is transforming spaceflight economics and ambition. For over half a century, rockets were treated like disposable packaging, built for one brutal flight. An engineering masterpiece was filled with propellant hurled skyward and then abandoned to the ocean. Imagine flying an airliner from New York to London and then shredding it on arrival. That was essentially how we approached orbit. For decades, build it, launch it, lose it. The price tag was staggering, especially for heavy lift vehicles and national flagship programs. A single Atlas V launch could cost well over $100 million each time. NASA Space Launch System missions push into the multi-billion-dollar range per flight. Yet after a few minutes of work, those massive first stages and engines were discarded. Complex avionics structures and engines worth tens of millions ended up on the sea floor. This disposable model made access to orbit rare, expensive, and limited to superpower budgets. The dream of frequent missions and large-scale exploration remained pinned down by simple economics. If every trip to space meant building a new rocket fleet, humanity would never scale. The obvious question emerged: how do you stop throwing away the most expensive hardware? The solution did not start with exotic materials, but with a daring change in mindset. What if the first stage could finish its job, then fly itself home for reuse? SpaceX turned that question into reality with the now familiar propulsive landing sequence. After stage separation, cold gas thrusters flip the booster to point engines back toward Earth. For some missions, a boost-back burn steers the vehicle precisely toward its landing zone. As it slams into the upper atmosphere, 4 grid fins unfold like giant metal waffle irons. These fins steer the falling booster, making constant tiny corrections for a pinpoint trajectory. Near the surface, a single Merlin engine ignites for the final landing burn. The rocket decelerates from supersonic speeds to a gentle touchdown on concrete or drone ship. What once looked like science fiction has now been repeated successfully hundreds of times. By early 2025, Falcon-style boosters had landed successfully more than 540 times. But propulsive landing is not the only path to recovery, especially for smaller rockets. Rocket Lab Electron lacks enough leftover propellant for a powered landing, so they went ballistic. After re-entry, the booster deploys parachutes, slowing it for a controlled splashdown in the ocean. A recovery vessel steams to the landing zone, cranes ready to haul the stage aboard. Rocket Lab even experimented with helicopter mid-air catches before shifting to streamlined marine recovery. These modern techniques stand on the shoulders of earlier recovery efforts from the shuttle era. NASA shuttle solid rocket boosters separated, then parachuted into the Atlantic for retrieval. Specialized ships, Liberty Star and Freedom Star, would race out to snag the floating giants. Crews then towed the casings back for a long, complex refurbishment process, proving reuse was possible. Landing a rocket is dramatic, but it is only half the battle in reusability. The real work begins once the stage is safe back on land, inside refurbishment facilities. Here, technicians treat the vehicle less like scrap metal and more like a patient. The first step is a detailed visual inspection, checking every panel seam and landing leg. Those familiar soot streaks you see on reused boosters hide a story of controlled violence. Underneath the surface, engineers use X-rays and ultrasonic scans to hunt for hidden damage. They focus especially on load-bearing structures, attachment points, and welds stressed during ascent and landing. The heat shield at the base and the grid fins receive special attention and replacements when needed. Then come the engines, the 9 Merlin power plants that carried the booster through ascent and return. Each engine is checked for performance data, vibration signatures, and any sign of thermal stress. Hydraulic systems for grid fins, landing leg actuators, and thrust vectoring all undergo rigorous testing cycles. Meanwhile, avionics bays are opened and flight computers inspected, updated, and prepared for another mission. Every sensor that fed data to guidance systems is calibrated again to ensure precise behavior in flight. Nothing about this process is casual. Each step is documented with aircraft-style maintenance discipline. The booster essentially carries a passport recording every launch, landing, repair, and modification in detail. Over time, that history lets engineers understand how hardware ages across dozens of high-energy flights. But reuse only changes the game if turnaround time shrinks from months to days. Turnaround time, the gap between landing and next launch, has become a critical performance metric. In the early days, each recovered Falcon booster spent months in refurbishment and testing. Process improvements gradually cut that down, first to around 100 days, then below 50. Eventually, routine reflights began occurring with turnarounds under 30 days for frequently used boosters. In early 2025, Booster B1088 set a stunning new record. It launched, landed, and then launched again in just 9 days between missions. That kind of cadence is where the financial magic of reusability really appears. Estimates suggest refurbishing a Falcon first stage can cost under 10% of building new. Those savings flow directly into lower launch prices and more ambitious mission manifests for customers. Today, a reusable Falcon 9 flight is listed around $67 million per mission. That price point has fundamentally shifted the economics of placing payloads and constellations into orbit. Without reuse, mega constellations like Starlink would be nearly impossible to deploy at current scale. Recovery also enables experimental missions where hardware can be inspected afterward to refine designs. Every returned booster becomes a flying laboratory, recording how real flights stress real metal. For companies operating fleets of rockets, this feedback loop accelerates reliability upgrades and design evolution. Some fleet leaders have already flown more than 30 times, rewriting expectations for rocket lifetimes. We are watching rockets transition from disposable artifacts into durable infrastructure assets for space. The revolution happening on ocean barges and inside hangars is reshaping the entire launch industry. Instead of building rockets, companies are increasingly operating rocket fleets with scheduled service intervals. This shift opens the door to more frequent missions, lunar infrastructure, and eventually human settlements. Catching a skyscraper falling from space is no longer science fiction, it is routine groundwork. Groundwork for building depots, stations, and cities that extend human presence far beyond Earth. The next giant leap will not come from a single heroic launch, but from reliability and reuse. If you want to keep following how rocket recovery evolves, subscribe to Beyond Delta 5. Turn on notifications so you do not miss the next chapter in reusable spaceflight. In upcoming episodes, we will unpack Starship recovery plans and next-generation reusable engines. From daring ocean landings to meticulous inspections, this hidden world is building our future among the stars.